We'll continue our discussion on optical amplifiers. So last time we looked at how for any optical amplifier we have this gain for the optical field, right, which happens due to population inversion that we induce in the medium due to some external pumping, right, either electrical or optical. And this gain we saw is typically a function of frequency or wavelength, right? And so the amplifier has some gain bandwidth. And we also saw that the gain typically also depends on the power, right? Because as you increase the input power, the gain doesn't remain constant, but with increasing optical power, the gain actually starts going down, because as the power in the medium increases, it causes more and more stimulated emission, which reduces the population inversion and hence reduces the gain, right? So let's discuss this gain saturation and how it's modeled in general for an optical amplifier. So again, let's say our amplifier has it's a medium of length L, right? We send in some input power, and then in the output it is amplified by some factor capital G, right, which is the gain of the amplifier. And inside the amplifier here, the propagation equation we can write something like this, right, where small g is the gain coefficient. So it's typically a function of frequency we saw, right, but also a function of the power, right? So let's say we have a single frequency here at some particular omega equal to omega naught. So let's consider only one single variable. So then this g we have at that particular frequency, right? So now it's only a function of power. And the power dependence is typically modeled something like this, right? We saw that the gain coefficient reduces by a factor of 1 plus P over P saturation, where P saturation is a particular power dependent on the type of optical amplifier you're using. Okay. But typically every amplifier will have some saturation power. So basically you can see as we increase the power, my gain coefficient is going down, right? Which means this overall gain that I'm getting, capital G, will actually be dependent on Pn. It won't be independent of P, right? So P out versus Pn won't be a straight line. It will be straight line for low input powers, but as you keep increasing the input power, it will start saturating. That is what we mean by gain saturation. But anyway, so we can model the gain saturation like this and actually integrate this equation to get the output power in terms of the input power, right? So let's just collect terms with the power on one side. So you can see that we get okay. So I'm taking this on this and this term on the left hand side. So when you do that, so you get 1 over P, which is here, this one, and then the next term will be 1 over P sat, right? Because the P's will cancel. Okay, and then on the right hand side, we just have this integral over the length. Right, so you'll get a log term here. You can see this will just be a linear P out minus Pn, and this will be G naught times L, right? And we just put P out equal to capital G times P in. So if you just do the simple integral and rearrange the terms, you'll get capital G is equal to okay. So we see that this gain, the output power divided by the input power, actually depends on the input power now, right? And furthermore, you also have this G on the right hand side also. So this is like a implicit equation, right? It's like a transcendental equation in G. Okay, and this G naught here is what is known as a small signal gain, that is e to exponential of this small G naught times n. Right? So if your power is very small compared to the saturation power, then you neglect this term, and then you can see the gain you get will just be e to the G naught n. So this capital G naught, which is e to the small G naught times L, is known as the small signal gain or unsaturated gain. So for P much smaller than the saturation. Okay, equivalently I can, because I know that P out and P in are just related by this gain factor, right? I can also write this so you can write in this in different forms. For example, if I just take the exponential, right, I can also write it like this. Okay, so this is somewhat this form directly shows you that, so for P in small, very small compared to P sat, this exponential factor will be very small, which means this factor will be close to 1 and G will be close to G naught. As you increase P in, this factor will start going down, right, and G naught will become less than G naught. G will become less than G naught, right? Sometimes you also write it in terms of the output power. So I have another factor of G here. I just write P in as P out by G. Okay, so what this means is basically if you plot this amplifier gain normalized to the small signal gain as a function of, let's say, for example, output power divided by the saturation power. Okay, so basically for low powers, okay, so when you are below saturation power, the gain is close to the unsaturated gain. So you start somewhere here, and then as you increase the input power, or if you want more output power from your amplifier, then the gain goes down. Okay. So typically you can see that sort of PSAT is a measure of how much power you can get out of the amplifier, right? So as you keep increasing the input power, the gain keeps going down, right? So there is some sort of maximum output power you can expect from the amplifier. It's not that if you keep increasing the input power, the output power will also increase. Okay, so P sat you can see sort of roughly how much power you can get of the order of that order of magnitude, because once the output power exceeds P sat, you can see that the gain is extremely low, right? So you're not enhancing the output power anymore. Okay, and this curve actually you can from here see depends on this unsaturated gain value, right? So for different values of the unsaturated gain, this curve is actually slightly different. So this is for G0 30 dB, and this is, let's say, 15 dB, and this is G0 equal to 10 dB. Right, 30 dB means a small signal gain of 1000. Right, 10 dB means gain of 10. So you can see that if you have a larger small signal gain, your saturation occurs earlier, right? Whereas if you have a smaller gain, it occurs slightly later. Okay? But you can see that actually, if you change the small signal gain, that is not changing how much maximum power you can get out of the amplifier. It's not changing that by too much, right? So that's still roughly like around P sat, maybe between 1 and 10 P sat is what the maximum power you can expect out of your optical amplifier. Okay, so P sat you can see that it's an important metric for any optical amplifier. Equivalently, you can plot G as a function of the input power. So let's say this G now dB versus the input power. So it starts from G0, the small signal gain, right, and it goes down like this. And you can see, okay, for example, at what point does it go down by 3 dB? Okay, so from this equation, you can check that that happens at an input power of roughly 0.7 P sat divided by G0 by 2. Okay, so basically in this equation, if you put G equal to G0 by 2, that's 3 dB lower, right? Right, so if you put G equal to G0 by 2 in this equation, you'll get P out okay, and G is also again now G0 by 2. Okay, so if G0 is much bigger than 1, which typically it is the case, right? At least you have a gain, small signal gain of 10 dB or more, right? Otherwise, I mean, you can see that there won't be much point of using an amplifier, right? So the small signal gain typically is minimum at least 10 dB or higher, up to 20, 30 dB. Okay, so then you can ignore this 2 with respect to the G0. So then I can write this as ln of 2 times this G0. So G0 and G0 will cancel from the numerator and denominator. So I get log of 2 times P sat. Okay, so in other words, this curve here comes down to 0.5, roughly at log 2 times P sat. this value here is log 2 times Pz. Of course, it depends on G naught, but this variation is not too much, right? If you see we get changing G naught by a factor of 100, this doesn't change too much. So this approximation is quite good. Okay, and if I divide by G or G naught by 2, I get so log 2 to the base E is roughly 0.7. If I divide by the gain G, or which is G naught by 2, that's the input power at which the gain goes. Okay, so I hope this type of general feature you get with any amplifier in general, but especially for the optical amplifier that we are discussing. So if you want large gain, typically you have to work at powers much below the saturation power. Or another metric is what is the maximum power I can get out of the amplifier is typically of the order of feedback. Right. Okay. So apart from this, the amount of gain or power that I can get from the amplifier, another important metric, especially for communication link, is noise, right? You know that any amplifier, in addition to providing gain, it adds noise, right? So no amplifier is perfect. So every time you add an amplifier, you actually end up degrading your SNR, right? So the noise figure for an amplifier is also an important metric. Okay, so noise figure, as you know, is defined as the ratio of the input SNR to the output SNR. Okay, so of course, so let's say I have some amplifier with gain G, I have an input power here, output power is amplified by factor G. However, if I look at the SNR, okay, that typically, so SNR at the output is lower than the SNR at the input. So this factor is more than 1. So you can think about this as, so what is happening is, so let's say you have, the amplifier is obviously amplifying your signal. Let's say it has some noise along with it in your signal. The noise also gets amplified by the same factor G, right? So if only this was happening, then your noise figure should be 1, right? Because input SNR should be equal to output SNR. Both the signal and noise have been amplified by the same factor. So the SNR should remain the same. But actually what happens is that the amplifier adds its own noise. Okay, so in addition to amplifying the input noise, it adds its own noise. So that at the output, the noise is more than G times the input noise, right? So that means you can see that at the output, the SNR will be lower than what the SNR is at the input. And this fact is true for any kind of amplifier. It could be any electronic amplifier or optical amplifier. in this case. So recall that when we were discussing receiver noise, right? We said that this thermal noise is enhanced by this factor of noise figure for electronic circuit that we use for the receiver, right? And now we'll involve this noise figure for the optical amplifier. Okay, so in terms of the spectrum, so let's say my input signal is at a particular frequency here, right? Some u0. So at the output, what happens is, of course, this is amplified, right? So this is, if it's at P in, now it goes to G times P in. But along with that, like there is some noise spectrum here. So there is not some noise. So my signal is at a signal some noise here, which so let's say my input signal was so my input signal will also have some noise, right? In the perfect case, it will at least have short noise, right? Because again, light is composed of photons. We know that. So the minimum amount of noise is in any optical field will be the short noise. Okay, so there will be some minimum amount of noise here, which is the short noise. So that gets amplified. In addition, you add some extra noise to amplify itself. Okay, so the signal to noise ratio that typically goes down. The function of frequency. We can also think about this in terms of the electric field. So P in, let's say, so if my electric field of the input light is some E in, so basically we are saying P in is proportional to mod E square, right? And then at the output, right, my field is enhanced by a factor square root of G, because G is the power gain factor, right? So not only does my signal get amplified by this factor, but I add some noise here, which for an amplifier is typically spontaneous noise. Right, so again, the amplifier works on this gain due to population inversion, right? So the gain that is occurring here is due to stimulated emission, but there is also spontaneous happening, which gives me, which typically gives me photons at random frequencies and phase, right? Which is what this noise component here is. So that is what this spontaneous emission field is denoting. So in addition to amplifying this, I have this noise. Okay, or so the power at the output is mod square of the field at the output. So that's mod square of this, right? So you can see the first term will of course be G times mod E in square, that is G times P in, but I'll have additional terms, which is what is my noise. Okay, so typically what is done is to limit this noise figure as low as possible, right? You can see that, so the noise is distributed over broad bandwidth typically compared to my signal, right? So typically what is done is that after the amplifier, I put a narrow band optical filter. Okay, so after the amplifier, I typically put a narrowband optical filter of some bandwidth delta nu optical to cut out basically the noise beyond this particular band. Okay, so if I put a narrow optical filter, I can cut out most of the noise, whereas my signal is typically narrow band anyway, so it will go through my filter. So typically, to limit the degradation in SNR due to the optical amplifiers, we typically use a narrowband optical filter after the amplifier. Okay, so let's try to estimate what this noise figure would be typically. So at the input, my SNR is given by. So again, the SNRs we are talking about will be in electrical terms, although we are looking at an optical amplifier. Finally, again, for a communication link, at the receiver will be detecting it on a photodiode and then some receiver circuit, so we get an electrical signal. So we write it in terms of the photocurrent that would be generated from this optical power. Okay, so okay, so the SNR at the input would be the square of the photocurrent that I will get if I send this amount of optical power onto a photodetector, divided by the noise current or the variance of the photocurrent that I get. Right? This is what we have been doing when, for example, when we discuss receiver noise. So the photocurrent will just be responsivity of the detector I use times the input power, right? And what will be the noise? That will just be the so now we are looking at the noises in my optical signals, right? So when we were discussing receivers, for this noise current here, we looked at the noise mechanisms in the receiver, right? The short noise, thermal noise. Here we are looking at the noise present in my optical signal. Okay. So in the optical signal, as you said, typically we only have short noise, right? Of course, we saw that from a laser source, typically we have this relative intensity noise spectrum, right, which has some dependence with frequency, right? So something it looks like this, the noise spectrum versus frequency, right? But typically, if the laser is good, right? So typically, in most of the range, this noise is flat, right? And this level was determined by short noise, photon short noise, right? So this peak was the relaxation oscillation peak, and then this low frequency noise. But in most of the range, typically it's given by the short noise. So for the denominator here, we can put basically the short noise in the optical field here, which will give me a noise in the photocurrent detected. Right? So now we are not taking any receiver noise, we are just seeing how much noise I will get from my optical signal itself. Okay. So again, so that's dependent on the optical power that I have, like the same expression that we had used for short noise. Right? So basically, this is just short noise, and so delta F is so basically the noise within the detector bandwidth. It's delta F. Okay. And then we put the responsivity equal to this in terms of the quantum efficiency. Okay. And we just put quantum efficiency equal to 1. That is an ideal detector. Because again, remember, our aim is to quantify the noise in my optical signal. We're not worrying about the detector at this point, right? So we can take an ideal detector. Right? The detector is just here taken to write the noise in terms of electrical parameters, in terms of the electrical. Right? So we take an ideal detector here. So if we put this substitution here, you can see that the input SNR I can write in terms of the input power divided by the photon energy times the bandwidth. Okay. You can also think of this now in terms of like sort of the optical SNR, right? So this is the optical signal will depend on the optical power, and this is the sort of the noise in the optical power which depends on the bandwidth. I'm looking at my measurement bandwidth, and then the noise level is sort of like the energy of one photon. Anyway, okay, so that's how I can quantify the noise in my or the SNR of my input signal, right? So if I have an optical signal input, which is quantum limited, so to say, then only noise is short noise, then the SNR will be given that. Okay. I hope this discussion is clear. Okay, and now we'll try to compute the SNR, the output, right? And then basically try to compute the noise. Okay, so for the output, we need to take this noise source due to the spontaneous emission. Okay, so again, we've already discussed some noise sources, right? Like for example, in the receivers, we discussed electronic noise sources like thermal noise, short noise. And basically, typically how we model is that we take some, it's modeled as a random variable in time. So we take this autocorrelation function and then take the Fourier transform to find the noise power spectral density, right? And then the total noise that comes in my detection is the noise power within the detection band. Okay. Similar you can do here, same thing. Okay. So for any kind of noise source, you can do the same kind of treatment. So if you look at the noise spectral density for spontaneous emission noise, okay, so it also looks sort of like white kind of noise, especially if, let's say, we are filtering over some bandwidth here, right? So basically we are cutting out everything out this bandwidth, right? So let's say my center frequency is mu naught, which is my signal frequency, and then I have bandwidth delta nu optical for the optical filter. So if I look at the noise power spectral density of this spontaneous emission noise, that looks sort of flat. So typically it's flat over the typically gain bandwidth of the amplifier I'm using. Okay. So depends on the type of amplifier you use, but typically the optical filter you will use will be much narrower than the total gain bandwidth of the amplifier. Right? It will just be around your particular signal wavelength. So over the optical filter, bandwidth is definitely flat. And this value here depends on the gain of the amplifier times this factor, which is the spontaneous emission factor, times the photon energy. Okay, so the level of this noise spectral density depends on the gain, photon energy, and this spontaneous emission factor NSP, which is basically the amount of population inversion you have. So it's N2 by N2 minus N1, where N2 is the number of atoms in your excited state. Okay. So for the optical amplifier, of course, we have population inversion to get gain, which means N2 is greater than N1, right? So the denominator is, of course, positive, right? So you can see that, so you start getting population inversion just when N2 exceeds N1, right? So the onset of population inversion is when N2 is equal to N1, and you can see at that point the denominator is 0, which means this factor is very large, right? So this noise is very high. So when you're just close to population inversion, the noise is actually very, very high because your stimulated emission hasn't kicked in yet, and you're dominated still by spontaneous emission, right? Now, as you go to more and more population inversion, as N2 becomes larger and larger than N1, this factor goes down, right? And you can see the ultimate limit is if I put all the atoms in the excited state, which typically you don't reach that limit ever because again recall that your stimulated emission is pushing atoms down back to the ground state. But anyway, so the ultimate limit here you can see if N1 is 0 and you put all the atoms in N2, then this factor is close to 1, right? So that's the lowest this NSP can be, right? So NSP is always greater than 1. And the more population inversion you have, the closer it is to 1, or the lower your noise. So this is known as the spontaneous emission factor. Okay, so basically the total noise power that I get, the noise power that the amplifier is adding here, sort of I can write it as this power spectral density multiplied by the bandwidth of my optical filter. Right, so this area under this is the noise added by the amplifier. Okay, so let's go back to sort of this expression here, right? So again, if I want to now look at the output SNR, I can write it as square of the output photocurrent, which means the power coming out of the amplifier if I send that to the same photodetector, divided by the variance of the photocurrent, right? So this is delta I out, right? Variance of the photocurrent. So there's a question: why are we taking only spontaneous noise for amplifier? Because what other noise are you thinking about? Right. So an optical amplifier works by this principle. Right. There are different types of amplifiers, but all of them work on this principle where you have more atoms, or in case of SOA, charge carriers, electrons in the higher level compared to the lower level, so that stimulated emission dominates over absorption, right? And you get net gain. And stimulated emission, it causes emission of photons in the same frequency and phase and direction as my incident photons. So all of them is giving me just enhancement in the signal. So the only noise component which is not adding on to my signal is a random recombinations here due to spontaneous emission. What other noise sources are you thinking about? For optical amplifiers, basically this is the only noise source. How the source RIN. So yeah, we just talked about this, right? So typically we assume, so here we've assumed that the RIN is dominated by short noise over most of the spectrum, right? Otherwise, ideally you have to integrate over the exact RIN spectrum, right? So then this expression is by sort of assuming that you have this flat line over the entire detector band, right? So there will be some correction because of this relaxation oscillation peak and some low frequency noise here, but typically that correction is very small. So that's the point. Okay, so maybe a more exact expression for this would be to integrate the RIN noise, the exact shape of the RIN function over my detector bandwidth, right, and then multiply by this average power or P. That will be my noise cost. But so here what you've done is basically said, okay, the RIN is mostly determined by the short noise over. Okay, I hope that's here. Okay, so clear why we are only considering spontaneous emission noise, because that's the only sort of noise. For electronic circuitry, right, like for what we were, for example, when we were discussing receiver noise, thermal noise, because again, so here the frequencies we are looking at are optical frequencies, hundreds of terahertz, right? Whereas, so these thermal noise mechanisms that we were looking at for receiver, for example, we saw that those fluctuations are up to a frequency of a terahertz, right? So when we are detecting the signal and now we are in the baseband frequencies, when we are working up to tens or hundreds of gigahertz, then those thermal noise mechanisms, etc., come in. But when we are looking at the optical noise at the optical frequencies, right, there is none of that thermal noise or anything. Only noise is this spontaneous emission. Okay, that's sort of another reason actually why optical amplifiers typically have better noise figures than any electronic amplifier you take. Okay. So typically any electronic amplifier you build, we tend to have noise figures maybe 10 dB or higher. Whereas for optical amplifiers, we'll see that noise figures can be as good as maybe close to 3 dB. Okay. So typical figures are maybe 5 dB, 6 dB, can be as low as 3 dB. And the reason is, again, the noise is only due to spontaneous emission, and we can limit the noise by using this optical filtering. Right? And you don't have these additional noise mechanisms that you typically get for low frequencies or electronic signals. Anyway, okay, so yeah, so let's try to compute this. So the output photocurrent, you can again write responsivity times the output power, and then from here you can write this as Okay, and now so you can see here we have three terms, right? So a plus b square, we have three terms. So the first term will be this times g times mod e in square, which is just p in, right? That's the first term, square of this. Right, so this you can see is just so this is like g times the input voltage. So this is just the signal gain that we are talking about. That's why we are using the amplifiers. Okay. Now the second term will be the cross term between these two. Okay, so you can think about, so again, my E in, so if I have a single frequency input, right? So this was something like, I can write this as some mod of E in times e to the I omega naught t, right? That's my field for the input. Whereas this spontaneous emission field, okay, so this I can write as something which has uh, a random frequency here, so delta omega and a random phase. Okay, so both this you can think of as some randomly fluctuating frequency and randomly fluctuating phase. Okay, so for example, my signal electric field looks like a nice sine wave. Right. Whereas if I look at the spontaneous emission field, that looks like some random fluctuations. Right? Again, sort of whose Fourier transform if I take, I get this noise spectral. Okay, so basically, so this cross term will be a meeting between this sort of coherent signal and this randomly fluctuating noise. So the cross term will be okay, where theta is the phase, this phase, random phase that I'm getting for this signal. So mod of this square, you can think of, I can write this as some square root of E or E CSP times the conjugate, right? So E in star plus ESP star now. So the first term will be E in times E in star, mod E in square, that's this, right? So this is basically my signal current. Then the cross term will be, so E in times ESP star plus ESP times EN star, right? So you'll have e to the I theta plus e to the minus I theta, which will give you a cosine theta. Okay, so this is the beating between my signal and the spontaneous emission noise. And then there will be a third term, which is sort of just the spontaneous emission noise. So this main current that I am getting is due to the meeting of the signal with itself, which is just the amplified signal that we want. Then the cross term gives me a beating between the signal and the spontaneous emission noise. Okay. And then the third term will be sort of the mod responsivity times mod of ESP. Right, so this mod of ESP square is basically like this this spontaneous emission noise power. Right, they say how much noise power is getting through my optical filter. Okay, so typically this second term, the cross term, dominates over this, right? Because you can see now, so typically the signal level is much higher than the noise, right? Right. So signal level is much higher than the noise level. So E in magnitude is much higher than ESP. Plus you have a square root of G also with this E in. Right. So this product of E in, so G times E in times ESP will be much bigger than mod ESP square. Right. So this cross term of the signal and the spontaneous emission will be much bigger than just the spontaneous emission square. Okay. So, and if I talk about basically the noise current being composed of these two, then this is the dominant component of the noise current compared to this. Right, so this is much bigger than this typically. You noted that down, come back to that. Okay, so I'm interested in the variance, right? Variance of the current, that is basically the noise here. So this is the value of the current, and so now this theta is a randomly varying quantity, right? So you can see that sometimes this will be positive, sometimes this will be negative, right? So this is a fluctuating current. So the average of this current will be 0, for example, right? So if I want to now know, but the variance will be non-zero. So if I try to calculate the variance of this, right? So basically, I take the average of the square of this, right? That's the variance. So the average of this is 0, just like for any noise process. But the average of the square of this, you can see, is not 0. So square of this will give me cosine square theta right? And average of cosine square theta is not 0 because cosine square theta is always positive. And you know that actually average of cosine square theta is half, right? When I take average of cosine square theta. Okay, and so this mod E in square is just the input power P in. Okay. Mod ESP is the spontaneous emission power, noise power here, right? Okay, so that we write as this spontaneous emission noise power spectral density. Okay, times now the bandwidth. Okay, now we are talking about the current, photocurrent here. Okay, so typically, so what will do? So when you send this signal onto the photodetector, right? So first of all, this will just come to baseband, right? Because the photodetector cannot respond at mu naught, right? So just like, so when you have this signal and you take mod square, this e to the I omega naught t goes away, right? the detector just gives you a DC signal. Similarly here, right? If you have some noise which is centered at nu naught, the nu naught is much higher than the detector bandwidth, right? So it's not responding to that. So this gets shifted to DC, right? So you have the noise now centered. Once you detect it on the photodetector, your current, so the noise in the photocurrent is now centered at 0, right? And if your detector is able to detect the whole of this bandwidth of the optical, then you'll have this whole bandwidth here. But typically, the detector will have its own bandwidth delta f, right? Which we, for example, used to compute the input SNR, right? We had a delta f in the denominator, which was the detector bandwidth, the electronic detector bandwidth. Similarly, so when I detect this output signal from the amplifier on the detector, right? So typically the detector bandwidth will be less than this optical filter bandwidth, right? Because again, optical filters, you're talking about optical frequencies which are much higher. Right? So typically this optical filter bandwidths will be maybe at least few hundred gigahertz. Okay, so the optical filter bandwidths are typically few. The narrow optical filters you're talking about are still like few hundred gigahertz, or like at least a couple of nanometers, for example. Okay. Whereas electronic detector bandwidths you're talking about are like 10 gigahertz, 20 gigahertz, right? So the electronic, so basically this you shift to baseband, right? And then out of this you slice out only the part which comes in within the detector band. So when you translate this to baseband, actually, so yeah, it will go from minus delta nu optical by 2 to delta nu optical by 2, right? But your electronic detector bandwidth delta f will typically be much smaller than this. So finally the noise that ends up in the photocurrent will be this noise power spectral density of the spontaneous emission divided multiplied by 2 delta f, right? From minus delta f plus delta f. Because this is more like a two-sided power spectral density for the electronic detector, right? I hope that's clear. So basically, this is this noise spectral density times 2 delta f. What shows up in my photo? Okay, is that clear? How the values of these terms? So then we can see here what we'll end up with. So this 2 cancels out with this half. And then this 4, we sort of split it into, we write this as 2 times, right? So this is my signal current here times okay, so now this directly shows you how this is a beating between the signal and the noise. Okay, and this last term will be, so this is, you can see, will be something proportional to this S square, right? So this will be, so if I want to look at the variance of this last portion of the photocurrent, right? So here you can see this part of the noise current is proportional to the noise power, or S. So the variance square of that will be proportional to S square. Okay. Okay, so typically that term will be much smaller than this term. Little bit later on, maybe in the next class, we'll also we'll include this term and see its effect also. But for now, basically, we're just saying that this beating between the signal and the spontaneous emission is much bigger than just the spontaneous emission squared. Okay, so we are neglecting the it should be proportional to s squared. Anyway, so I hope this is clear how we get this, the variance of the photocurrent to be this. Okay, so now we are basically done, right? Because now we have, so now we can write the output SNR, because I know, right, my output photocurrent here, and also I know the noise. So the SNR at the output of the amplifier. Okay, so now the average photocurrent square here is just this first term. Right? And then the variance in the photocurrent is this term. Okay. So you can see this comes out to be okay. So again, this also sort of makes sense, right? Physically, because so now what is the output SNR? Is the output power, which is gain times the input power. That's the signal power at my output. Divided by what is the noise power? This is the spontaneous emission noise within the detector bandwidth. So, makes sense? So now again, finally, now we can compute the noise figure. So let's write the expression for the input SNR that we had. So the input SNR was this, right? And the output SNR is that. So now the noise figure I can write from here. So yeah, you just put in these. Okay. So of course, the electronic bandwidth cancels out, because again we are computing the noise figure of the optical amplifier, which should actually not depend on the parameters of this electrical detector we are using, right? The electrical detector is just to characterize the noise in terms of the electrical power. But so anyway, so you can see that cancels out, and we can also put in. So for example, we had an expression for this noise spectral density of the spontaneous emission noise, right, which depended on the gain and this spontaneous emission factor times the photon energy. So if you put this expression for the noise spectral density for spontaneous emission, so we can see that the photon energy will also cancel out, and you will just end up with okay. And typically, again, the gain values that we'll be using for the amplifier will be typically, let's say, maybe at least 10 dB, right? So this G will be at least 10. So G minus 1 will be almost G. So this will just be 2 times the spontaneous emission noise or spontaneous emission factor. So for G much bigger than 1. Okay, so you can see that for an optical amplifier, the noise figure is just given by the spontaneous emission factor, which was again recalled. So this was N2 by N2 minus N1. So how many atoms you have in the excited state versus the. So again, NSP is greater than 1, which means that your noise figure is greater than 2. Right? Because NSP is greater than 1, so the noise figure is 2 times NSP. So you can see noise figure is always greater than 2. Okay, so for an ideal optical amplifier, the least amount of noise you can add, right, a noise figure of 2, which means your SNR degrades by a factor of 2. That's the best you can do. So 3 dB. Okay, so typically for the practical optical amplifiers that are used in the links, typically they're like about 6 dB, maybe 6 to 8 dB are the usual typical ones that are used. But you can also get some fancy ones which are almost close to 3 dB limit. And typically these values for optical amplifiers, as I said, are much lower than electronic amplifiers. If you look at the noise figures for electronic amplifiers. Okay. So I hope that discussion on noise figure was clear. So now let's see. So we saw that how we can use these optical amplifiers at various places in my link, right? So like at the transmitter as a booster amplifier, or along the fiber link as inline amplifiers, or at the receiver as a pre-amplifier. So let's look at maybe each of these cases. So starting with a pre-amplifier at the detector. So how does that help me? For example, so I would use that only if, for example, it can help me obtain a lower bit error rate for the same optical power, right? So you have your transmitter, then your fiber link, right? And now at the receiver, instead of directly detecting on a photodetector, I first use an optical amplifier. So this is my pre-amplifier. Optical. Right? We also discussed some amplifiers in the electronic circuitry, but that is after photodetection. This is in the optical, so again, amplifying the optical signal itself before photodetection. So again, after the optical amplifier, we typically have some optical filter. Then we send it to my photodetector, giving my photocurrent. Okay, and so I have some P received here, right? This average power received, so which is how we calculate the sensitivity So for example, I need some minimum power here to get a VER of 10 to the minus 9. Right? Now, so if I insert this thing before my photodetector, can I improve my sensitivity, for example? So can I now get 10 to the minus 9 VER with a much lower receive power? Right? That is the question. So again, so now this photodiode and receiver circuitry will have some electronic bandwidth delta F. Okay, so typically use of a pre-amplifier, right, can reduce, can improve my receiver sensitivity, which means like reduce my receive power required by roughly like order of magnitude. Okay, so I can get the same VER like 10 to the minus 9 with now 10 times lower receive power with typical with a pre-amplifier. So let's see how that happens. So typically, for example, if you don't have this, you directly photodetect. Let's say you're using pin diode in the thermal noise limit. Typically, we saw that the sensitivity was so roughly like 2000 photons per bit, right? Is where typical receivers are operating at. If I use a pre-amplifier, typically I can get this down to like maybe 200 photons per bit. 100 to 200 photons per bit. Okay. So let's see how that comes about. So again, we call this Q factor, right? So for 10 to the minus 9 VER, I need a Q of 6, right? So again, now consider an IMDD link. Okay, so this is equal to 6 for VER 10 to the minus 9. Okay, so again for IMDD, the photocurrent for bit 0 I can assume 0 on average. Photocurrent for bit 1 is again responsivity times the power in bit 1 or 2 times responsivity times average optical power AC. Okay, and then if I look at the noise current, so for bit 1, right, it's what we just discussed, right? So I have some optical signal coming here. This amplifier amplifies the optical signal but adds its own noise. Okay, and then when we photodetect, we'll get a noise in the photocurrent corresponding to the noise in the optical power, which is what we just discussed, right? When we were computing this noise figure for the amplifier, we calculate the SNR at the input and output. So basically the same thing, right? So we are now actually detecting on a photodiode, and basically what we are saying is that because of the use of this pre-amplifier, we are boosting the optical signal up, right? So now my optical power is high enough that my short noise in the optical power is dominant over the thermal noise in my electronic detector. Right. So, for example, when we were discussing APDs, we saw that because of this multiplication gain, right, we typically go into the short noise limit because now the short noise becomes higher than thermal noise. Okay. Similar thing is happening here, but now for a different reason, because now instead of like multiplying sort of the current here, the optical power is being enhanced before photodetection. And since the photocurrent is proportional to the optical power, and the short noise recall is proportional to the optical power. So now my optical power has been enhanced because of this amplifier, so that thermal noise of the electronic detector is insignificant. And that's how we are getting this improvement. Right? Again, because recall when we were discussing just the receiver noise, we discussed the two limits of the thermal and the short noise limit, and we actually saw that if we could work only in the short noise limit, we could get a better sensitivity, right? In terms of photon per bit. Okay, so then for bit 1, right? Again, now my the noise current is composed of this beating between the signal and the spontaneous emission. So we had just discussed, right? And we could also include now just the spontaneous emission squared, which we typically neglected. So typically this would be bigger than this, but we can include that also if you want. Whereas for bit 0, I have no signal now, right? So this is just the spontaneous emission square. Okay, so for bit 0, we just have the spontaneous emission noise on its own. Whereas for bit 1, we have this beating of the signal and the spontaneous emission noise, which is the dominant one. Okay, and so we had just derived expressions for this, right? So, for example, the beating between the signal and the spontaneous emission noise, the variance of that was this, right? So we had a P in. So we had a P in that expression, where P in was the input power to the amplifier, right? And so here basically that's the power in bit 1, right? So this is the same expression that we just derived a few minutes ago. And for the spontaneous emission squared, okay. So instead of this signal G times P1, now we have the spontaneous noise beating with itself, right? So what is the power here instead of the signal power? Instead of that, we'll have the optical power within the optical noise power within this optical filter bandwidth, right? So if I replace this by SSP times delta mu optical, then I get this expression. Okay, so instead of the signal beating with the noise, now with the spontaneous emission, now we have the spontaneous emission power, which is given by this beating with itself. Okay, so that variant current will come out to be this. Okay, basically in this expression we replace G times P1 with S is P10. I hope that's clear. Okay. So just like recall when we had computed the receiver sensitivity for direct detection, when we just had the receiver, right? So we put in these expressions for the these currents and the noise currents in terms of the optical power here, and then solve this equation to get the optical power in terms of the other parameters, right? And that would give me my sensitivity. So same thing we'll do here, right? So I1 will put this, Then for sigma 1, sigma 0, we can put it in terms of that. Right? So sometimes this is written in a different form. So if I put responsivity again equal to quantum efficiency of detector times this Q ratio. Now I have to take the quantum efficiency of the detector because now I'm using a real actual detector, right? So the quantum efficiency of that detector now comes in here. Okay. And also this spontaneous emission noise spectral density S, recall, is G minus 1 times this NSP times H nu, right? And recall the amplifier noise figure was 2 times NSP, so I can also write this as, and if I say G is much bigger than 1, I can write this G minus 1, I can just approximate by G, and I can write this as G times Fn by 2 times H nu. Okay, so that's my the spontaneous emission noise spectral density in terms of the actual parameters that I can measure, like the amplifier gain, the noise figure of the amplifier, and photon. Okay, and also you replace this for the responsivity here in terms of the quantum efficiency. Okay, anyway, so yeah, so you have this expression now in terms of, so P1 again is 2 times average received power. So I1 has P received, and then sigma square of that. So in sigma 1 we have a P received. Okay, so I put that here and then solve for P received to get okay. So now my receiver sensitivity, so again for a given Q, so let's say Q equal to 6, I'll get what optical power I need. Now depends on noise figure of the optical amplifier, receiver bandwidth, the electronic receiver bandwidth, and now this ratio of the optical filter bandwidth to the electronic receiver bandwidth. We can write it in terms of the photons per bit, right? Like the sensitivity in terms of photons per bit. So if I write again the receiver power, so again I will encourage you guys to derive this expression. So from starting from these expressions, put it into this expression for Q, and then solve for this receiver power to get. So in terms of average number of photons per bit, I can write the receive power as number of photons per bit times photon energy times bit rate. Right? And again, recall typically the electronic filter bandwidth, the receiver bandwidth here is typically set as roughly like V by 2, right? So this is the 3 dB bandwidth of the electronic receiver here. So that's roughly, right? Say it goes down to 0 at B, and this delta F is typically V by 2 roughly. So two times. Okay, so if I substitute, so here you can see that if I divide by 2 times S2 times delta F, Q times delta F, then I'll get the average number of photons per bit required to be now I can write in terms of the bit rate here again. So delta F I put B by 2. Okay. So you can see that if you want a high sensitivity, which means your receiver can give you a bit B or 10 to the minus 9 with a lower number of photons per bit, then you want a low noise figure, right? Which means your amplifier is good, it doesn't add too much noise. And your optical filter should also be narrow, right? Because the ratio of the optical filter to the bandwidth is also coming in. Okay, so for example, if you plot this receiver sensitivity now, average photons per bit. Again, so now our metrics are B are 10 to the minus 9 or Q of 6 as a function of this optical filter bandwidth normalized to the bit rate. Okay, so you get curves like this. So of course, as the optical filter bandwidth increases, the number of photons per bit required also increases. Okay, these different curves are for different values of noise figure. So the best is this. So Fn is 3 dB. That's the best you can do, right? So typically, so let's say bit rate is around 10 gigabit per second. Optical filters are at least, as I said, few hundred gigahertz, maybe 1 terahertz or more. So you're typically in this range. Okay. So you can see that. So this is for 5 dB, 7 dB. You can see that the sensitivity typically is around 200 photons per bit. Okay, and so for example, if you were not using this pre-amplifier and directly detecting, and then typically you are much higher, right? 2000 photons per bit. So I'm able to reduce the power requirement or equivalently the number of photons required by an order of magnitude by using a pre-amplifier. Okay, so you can actually finally see that it actually does not depend on the gain of this amplifier, right? So sensitivity here actually does not depend on the gain. It actually just depends on the noise figure, right? So you can see how noise figure is actually, especially for communication links, is even more real or important quantity than the gain, right? Because finally the gain is actually not figuring here, only the noise figure. Because again, recall the finally important quantity is the SNR. Anyway, so we're clear on time also, so we'll stop here. Any questions? Okay, so the only approximation we used was that G was large compared to 1. So as long as your amplifier gain is, let's say, at least 10, it doesn't matter if it's 10 or 100 or 1000. Right? The sensitivity only depends on the, does not depend on the gain. So it helps if you have an amplifier here, but it doesn't help if you have a very large gain. Right? All you need is some, at least like an order of magnitude gain in the power, but beyond that, it doesn't help you at all. Right? So it helps you to have an amplifier, but beyond that, it doesn't help you to. Right. So, for example, you might imagine, let's say, oh, if this is giving me an improvement, why not let me add one more before this? Right? Would that give me more improvement? No, right? Because more gain, you can see, does not figure, that will actually worsen my noise figure, right? So this will increase and the sensitivity will actually. So it's kind of interesting that. So the only reason this is helping is you're going from the thermal noise limit to the short noise limit, right? So that's why you just need this amplifier. But beyond that, once you have gone into short noise limit, now if you keep increasing the power, actually it's not helping.